All right, so now we're down to the subject that we're going to spend more time on in this course than any other because it's probably the most important thing that we're going to cover, which are derivations. And a derivation is a way of showing that given a set of sentences, we can derive something from those sentences using certain allowable rules. And because of the way that these derivation systems are set up, what this shows is that if we take an argument and we start with the premises of that argument, if we can derive the conclusion of the argument, then that argument is valid. It's a valid argument, which is a very important property that arguments can have, right? Now, when we do these derivations, we might be doing them for two reasons. One might be to establish to ourselves or to convince ourselves that a certain argument that we've been presented with is in fact a valid argument. Another reason might be to show this as a proof to someone else who knows how to read these kind of things, which will be most people working in logic or math or computer science, that a certain argument is in fact a valid one. And if you're maybe if you're showing this to someone who doesn't know how to read a derivation, it'll give you some kind of guidance in how to formulate like an English language proof that would convince them in English that an argument is valid, right? So let's go ahead and take a look at an example. We're going to start with some pretty simple examples where you can kind of see intuitively that the argument is valid. And we're going to show how you could go about formally proving that with a derivation. And then we're going to move on to some more difficult examples where maybe by looking at it, you wouldn't know that it was actually a valid argument. And that's where derivations really pay off because they help you to establish that something like that is in fact a valid argument. All right. So let's take a look at this example here, and let's talk first about what the different parts of what we're looking at are. So this is our derivation so far. A derivation is just a set of sentences, right, where each one follows from the sentences before by the use of certain rules. So this is what we have in our derivation so far. And these are both assumptions, which is why I write IAS over here. And these represent the premises of the argument that we're evaluating. So they're what we start with. So what we have over here, this is where we're going to write on the right-hand side in this column, these are going to be the justification of each line. In other words, where we're getting that line from, where we're allowed to have it why we're allowed to have it in the proof. This vertical line, this horizontal line, this separates the premises of the argument, the initial assumptions that we're working with, from the rest of the derivation. These numbers on the left, these are just the line number to help us keep track, and that'll help us to write in our justifications over here, as we'll see later. And this vertical line is what's called a scope line, or an assumption, sometimes called an assumption line by other textbooks. And that'll help the reason why we use that, it'll become more apparent tomorrow when we start working with subderivations. They help us to keep our subderivations straight. Now notice down here on the bottom, we've written in the goal that we're working towards, and this is the conclusion of our argument, okay? It's not a part of our derivation yet. We're just putting it down here to let ourselves know that that's what we're trying to get. That's what we're trying to reason from these assumptions and show that this conclusion follows, but we don't have that conclusion yet. So notice we haven't given it a number yet because we don't know how much stuff is going to have to go in here before we have this. And it's not part, like I said, it's not part of our derivation yet, so it doesn't have a number and it doesn't have a justification yet. If we knew how we were going to get it, maybe we could start writing the justification in, but we don't know that yet, so it doesn't have a justification. It's just down here to let us know that it's our target. All right. So, how should we start doing this? Well, a natural derivation system or a natural deduction system like the one we're working with, SD or Sentinel deduction, its rules are made to mirror the way that we would naturally reason about an argument, or the way that we would naturally go about evaluating an argument. So the one way to get started is to kind of look at this and read more or less what it says in English to convert the connectives back into English. And a lot of times it'll become apparent from doing that what it is that you should do. So what does this say? It says we have P and Q, so P and Q, and if P, then Q and not R, all right? And we're trying to get not R. So what's the first step we should do here? Well, we should do conjunction elimination. So because we have P and Q on this line, we're able to write P on this line. And it's pretty obvious why a rule like that would exist. This is something like I have cats and I have dogs. Well, if I have cats and I have dogs, then I have cats, right? And we're over here, we have to say how we got that line. Well, we got it by using the conjunction elimination rule on line 2. Okay? Now, how can we proceed now? Well, we have the antecedent of this conditional, so we can go ahead and apply the conditional elimination rule. Here, we had to use 2 lines to obtain this goal, so we need to write 2 numbers over here. The number that the conditional itself was on, and the number that the antecedent of the conditional was on, as well as citing the rule that we used, which is conditional elimination. Now we're actually ready to go ahead and finish this and get to conclusion. And we're going to do that by doing the same thing we did on lines 2 and 3. So we're ready to actually add this to our derivation now, so we're going to go ahead and give it a number. And we got that by doing conjunction elimination on line 4. So this proof is done now. We've shown that by the steps that we're allowed to use in this system of derivation, we can in fact get not R, starting with these assumptions. Okay. And notice we have a lot of blank space in our proof here. That's perfectly okay. It's a lot better to have more space than you need, or have a gap in here, than it is to run out of space and wind up with like a mess in here where you have to do a bunch of erasing.